In previous lecture, we derived momentum equation for control volume using Reynolds transport theorem. Okay, so we had this equation there, summation over all external forces is equal to d by dt cv vxyz rho dv plus integral over control surface vxyz rho vxyz dot dA. Okay, so to derive this, what we used was Newton's second law of motion. Okay, and since we know Newton's law of motion holds true only for inertial frames of reference. Inertial frames of reference are the ones that are non-accelerating. Okay, these are non-accelerating frames. Thus, let's say this is 1. This 1 holds true only for inertial frames of reference. Okay, but you will encounter certain problems where the system is accelerating and you will be left with no other choice but to take control volume on the system, and that control volume will also be accelerating with your system. Okay, so then we cannot, since this Newton's second law cannot be used for accelerating frames, and in that case, so let me just write it first. So for problems where the system is accelerating, we are left with no other choice but to take control volume accelerating with the system. Okay, now in those cases, since Newton's second law does not hold true, we need to change or modify our momentum equation. So this momentum equation 1 for non-inertial frames of reference. Okay, now why Newton's second law does not hold true for non-inertial frames? Let's understand this by taking one example. So let's say you are inside a car, okay, and then let's call it car A, and you are sitting inside this car, okay, and there is another car car B, which is moving with, let's say, a velocity v vector, and let's say you are accelerating with acceleration a vector. Okay, now since it is moving with constant velocity, according to Newton's second law of motion, there should be no external force applied on this car B. Okay, but if you see from the observer sitting in car A, which is accelerating with acceleration A, that person will see a pseudo force acting on this car B. Okay, and because of this pseudo force, that observer will say that this car B is accelerating or deaccelerating. Okay, so I hope this concept is clear to you. So in this problem, although there was no external force acting on car B, but still for the observer sitting in car A, this car B, some force is acting on this car B, because of which this car B would be accelerating. Okay, so how to modify our momentum equation, which was summation f external is equal to d by dt cv vxyz rho dv plus cs vxyz rho vxyz dot dA vector. How can we modify this equation? So we know that this is the velocity of the fluid with respect to the control volume. Okay, so let's say this is my control volume. Okay, so let me just use green color. So this is my control volume. Okay, let's say this control volume is moving with some velocity v reference, which is a function of time with respect to ground. So v reference is the velocity, is your time dependent velocity with respect to observer on ground. Okay, and let's say the fluid is flowing like this with velocity vxyz with respect to control volume. So let's say vxyz is the velocity of fluid with respect to control volume. Okay, so now if this is the case, then what can I say about the force on system? What can I say about the force on the system? We know that from Newton's second law, summation of all the forces will be mass of system times rate of change of velocity of system. Okay, now since we are arguing that this law is true only for inertial frames, so let's say this mass is m. This law is true only for inertial frames. Should the velocity, rate of change of velocity be the velocity in inertial frame, or should this be in non-inertial frame? So of course, since the Newton's second law holds true for inertial frames, this velocity should be in inertial frames. Okay, all right. Now let's assume that the time dependent velocity of system is equal to v capital X, Y, Z, which is a function of time. Okay, so let's not explicitly write function of time, but when I am writing v, x, y, z vector, you should know that this is a function of time. Okay, and also v, x, y, z vector, this v with small x, y, z is also a velocity vector which is a function of time. Okay, or let me just write it. So let's say this is a function of time, and also let's say this is also a function of time. Explicitly write. Okay, all right. Okay, so then this equation will become summation of external m d by dt v x, y, z t. Okay, so now what will be this v, x, y, z? Let's consider this. Let's say this is my control volume, and let's say there is some particle which is moving. There is some particle which is moving with velocity v, x, y, z with respect to ground, and v small x, y, z with respect to control volume. Okay, and this CV is moving with velocity v reference with respect to ground. So is there any relationship between among the three? So particles velocity with respect to CV is particles velocity with respect to ground minus particles velocity minus CV's velocity with respect to ground. Okay, we know this. Now what is particles velocity with respect to CV? Particles velocity with respect to CV is this v small x, y, z. What is particles velocity with respect to ground? That is v x, y, z. And what is CV's velocity with respect to ground? That is v reference. So what is v capital X, Y, z? That is v x, y, z with small x, y, z plus v reference. So we can write this v x, y, z equal to v x, y, z with small x, y, z plus v reference in this equation. Okay, so let's write it. So this becomes summation of external equal to m d by dt of v x, y, z plus v reference. Okay, where this v x, y, z is a function of t and v reference is also a function of t. Okay, and this summation of external is net external force on the system with respect to inertial frame, and here I have taken ground as the inertial frame, so let's say with respect to ground. Okay, so what will this become? M d by dt v x, y, z, which is a function of t, plus m d by dt v reference, which is again a function of t. Okay. So what does this equation tell me? What does this equation tell me? So this is the force that will be measured by CV, right? So this is the force measured by accelerating control volume for the system, right? And this is, so that, let's say if I take this term on the left side, this will become, or let's say so let's take this term left hand side, and extending the left hand side and the right hand sides, this will become m d by dt v xyz, which is a function of time, is equal to m d by dt v reference, which is a function of time, negative sign. Let me just write this as here, f external, which is system, f external of system with respect to ground, minus m d by dt v reference t. Okay. So this is the force measured by accelerating control volume or let me just write force on the system measured by accelerating control volume. This is the actual force on the system, and this is the pseudo force on the system measured by CV because of its acceleration. Okay. But using Reynolds theorem, we know that the force on the system measured by my CV is nothing but, so using Reynolds transport theorem for momentum, I know that force measured by CV, force on the system measured by CV, is equal to d by dt integral over CV vxyz rho dv plus cs vxyz rho vxyz dot dA. Okay. So I can equate this equation, with this equation, because this is the force measured by my CV, and this is also from the Reynolds theorem. We know that that the force measured by CV can also be written like this. Okay. So then let's say this is 1 and let's say this is 2, then 1 should be equal to 2. Okay. So this becomes summation f external minus m d by dt v reference, which is a function of time, is equal to, let me just copy paste this, okay. So this becomes equal to this. Now let's consider this term. Let's call it 3. Okay. So now in most of the questions, so what is this m first, by the way? This is the mass of the system. Okay. Now in most of the problems, what we take is, so consider this problem. So in most of the problems, what we consider is, we consider an elemental volume of CV and then integrate. Okay. So that's why I have to write this capital M in terms of the volume element. So how can I write it? I know dm is equal to rho dv and m is equal to integral over dm, so I can write this as rho over dv. Okay. And let's write acceleration of this volume element is the acceleration of elemental volume element. Okay. So then I can write m d by dt v reference is equal to integral rho a reference dv, right? Okay. So this is my 3 and let's plug in this value here. So what will this become? This will become summation over f external minus integral over rho a reference dv equal to d by dt vxyz rho dv integral over cv plus cs vxyz rho vxyz dot dA. Now since this is a general case, if I consider the special case where, let's say, my CV is inertial, that is, it's not accelerating, so in that case a reference will be 0 and the equation would become summation f external equal to this term. Okay. Okay. And this is the same equation that we derived for the CV which was not accelerating, which was inertial or not accelerating. Okay. All right. So this is the equation that we get if my control volume is accelerating. Okay. So this is the momentum equation when control volume is accelerating with accelerating and a reference is the acceleration of the volume element dv. Okay, so this is the expression that we get for non-inertial frames of reference. All right. Now let's understand how we can apply this equation by considering a problem. Okay. Let's consider this problem. This problem also I have taken from Fox and McDonald's Introduction to Fluid Mechanics. Okay. So what does this problem state? So let me just read this problem first. A vane with turning angle theta equal to 60 degrees. So this angle here given as 60 degrees is attached to a cart. The cart and a vane of mass something roll on a level track. Friction and air resistance can be neglected. So this time we don't need to consider Rx, Ry. Okay. At least, okay, we'll see whether to consider Ry or not, but we don't need to consider Rx because Rx is actually the friction force. Okay. The vane receives a jet of water which leaves a stationary nozzle horizontally with velocity something. So this is leaving with velocity something, and since this velocity reaching the velocity at this reaching this vane is not given, we'll assume that this comes with same velocity, that is 35 meters per second. Okay. The exit nozzle area is given to you. So this area is given to you with some value. Determine the velocity of the cart as a function of time and plot the results. So you have to find the velocity of the cart as a function of time. So this means that vane is accelerating, right? And you have to also plot the results. Okay. So let's start the problem by considering the control surface. So in the book, this is taken as the control surface. Okay. And the number for the control surface is also specified. So this is CS1, this is CS2, this is CS3, and let's say this is CS4. Okay. And the coordinate system is also defined. This is X and this is Y. Okay. Now if you see that this cart will be moving in only X direction, right? So that's why we only have to consider the forces along X axis. Okay. Alright. So let's just first write the equation, the momentum equation considering the non-inertial control volume. And by the way, this volume, since it is attached with my system and my system is accelerating, this control volume will also be accelerating, and that's why this control volume is non-inertial. Okay. And if this is non-inertial, we have to consider this equation, right? We have to consider this equation. Okay. So let us just copy paste this equation. Okay, so this was our equation. Okay, sorry, this was our equation, and we just argued that we'll only consider everything along x-axis. Okay, I can write this also as this. Okay, all right. Now again we'll assume that the flow is uniform, steady and incompressible. Okay, so if that is the case, this term would go to 0. Okay, now let's consider the forces acting on my control volume. So the only force which is acting on my control volume currently in the x-axis, in the along x direction, is the force due to atmosphere. Okay, the force due to atmosphere, right? And because of the symmetry of my control volume, or because of the symmetry of this atmospheric pressure, the atmospheric pressure would get cancelled out. Okay, so we don't have to consider the force due to atmospheric pressure. All right, now other than atmospheric pressure, the force due to atmospheric pressure, we don't have any other force acting on the control volume along x-axis. The only other force would have been the friction force, right? But in this question we are already given that we have to neglect the friction force and the air resistance. Okay, and since so apart from friction force, if this would have been accelerating, then because of the drag of air, this would feel an air resistance also. So that could also be other source of force along x-axis, but it is given in the question that we have to neglect the friction and the air resistance. So then there is no force, no external force which is acting on my control volume. Okay, so then this is also 0. So then what we are left with is minus, since only one fluid is there, rho A reference dV integral, this is along x, integral over control volume CV is equal to integral CS Vxyz rho Vxyz dot dA. Okay, and for this, these assumptions, we know that this will become summation over CSI V xyz dot rho Vxyz dot A for that CSI, right? Okay, now given that this control volume, since the control system is moving with velocity u vector, this control volume will also be moving with velocity u vector, then the acceleration of this control volume with respect to ground will be simply du by dt. Okay, so then I can write A reference x as du by dt. Okay, integral over dv. And consider this equation. So again this will be non-zero for control surface CS1 and CS3, right? Because for other control surfaces the velocity vector is 0, and due to that this term will not be contributed by those control surfaces. Okay, so this will be for CS1 and CS3. Okay, all right, so let's just write this as 1, this as 2, and this as 3, and consider these terms individually. So what would be 1? What is 1? 1 is minus rho du by dt CV over dV. Now since my CV, whole CV is accelerating with A reference, I can take this du by dt out of this integral. Okay, so then this will become du by dt and integral over dv. Okay, so integral over dv would be simply volume of your control surface, control volume. And what is rho times v? It is nothing but the mass inside your control volume. Okay, so one becomes, let me just write it. So this was minus rho integration over cv, a reference. Since we are taking the x component, the vector won't come, dv. And since a reference is constant for whole cv, we can take it outside of the integral. So this becomes, so one then becomes minus rho a reference dv. So this becomes a reference v, since integral over dv in the control volume v is nothing but the total volume of control volume, and this is nothing but mass times a reference, because rho times v is nothing but the total mass of system. Let's call it m. Okay, so this is my first term. Now let's consider second term. What is second term? Second term is over CS1. So what was my CS1? CS1 looked like this. The flow looked like this. Okay, with v vector, and this velocity is with respect to ground. Okay, this was CS1. Okay, and this CS1, since the control volume is moving with velocity u, the CS1 will also be moving with velocity u. Okay, so what is v xyz? This will be the velocity of fluid with respect to the control surface CS, which is nothing but the velocity of fluid with respect to ground minus velocity of fluid, velocity of CV with respect to ground. And this is equal to, what is velocity of fluid with respect to ground? That is v vector. And what is velocity of CV with respect to ground? That is u vector. So that's why v xyz is v minus u. Okay, for this CS1, for CS1. Okay, and since v and u are along x-axis only, v xyz along x for CS1 is v minus u. Okay, so then second term, which was summation CS1, okay, the summation will not come, v xyz along x rho v xyz dot a for that CS1 will be equal to, so what is v xyz along x in CS1? It is v minus u. Rho, what is v xyz dot a? So what is v xyz dot a? This is nothing but v xyz times a, and v xyz is v minus u. Okay, so this is my second term. Now what is third term? For third, let's just write it here. So now what is third? Third is on the control surface CS3. Okay, so it is simply V xyz rho V xyz dot A. Okay, on CS3. Okay, let me just draw CS3 again. So this is your CS3. And what was your CS1? This was your CS1. So what was the velocity of the fluid with respect to CS1? That was in magnitude, that was V minus U. Okay, alright. Now let's assume that the flow has the same magnitude here also. So this has the same magnitude here, and since it is given this as theta, so if this is the magnitude, direction wise I can write it like cos theta I hat to sin theta j hat. Okay, so this will be my velocity vector along this direction with respect to CS3. Okay, so then I can write Vxyz vector as V minus, and since we are taking the x part of this, what will be the x part of this V minus U cos theta plus sin theta j hat? That will be nothing but V minus U cos theta. Okay, then rho, and what is Vxyz dot A? This is nothing but Vxyz and A, and since it is the outlet, this will be a positive thing. Now what is Vxyz? What is the magnitude Vxyz? It is V minus U. It is V minus U, yes. So this is V minus U and A. Okay, so this is V minus U whole square cos theta rho A. This is my third term. So let's just write 1, 2 and 3. In this equation. So what is 1? 1 is minus rho minus m times A reference, minus m times A reference is equal to second plus third. What is second? Second is this thing, which is, so this is minus V minus U whole square rho A, minus V minus U whole square rho A, and what is third term? V minus U whole square rho A cos theta. Now I can write A reference, since we are interested in finding what is U as a function of t, I can write A reference as du by dt. Okay, and this is equal to minus Vu minus U square rho A. So let me just write it like this also again. By taking V minus U whole square rho A outside, this would become cos theta minus 1. If I take negative outside also, this would become 1 minus cos theta. Okay, so negative gets cancelled out with negative. Let's take this U term here. So this becomes du by V minus U whole square is equal to V minus U whole square. It is equal to 1 minus cos theta rho A divided by m dt. Okay, and now we'll integrate it from t is equal to 0 to t, and u will be from 0 to u. Okay, so we know that this can be written like v minus u to the power of minus 1 divided by minus 1 into minus 1 from 0 to u, and this is simply 1 minus cos theta rho a m t. Okay, what trick I have used here? So this is the integration rule. If you have, let's say, dx over x to the power of n, this is written as x to the power of minus n plus 1 upon minus n plus 1. Okay, so this is the rule that I have used here. So here n was 2, so it will be minus 2 plus 1, which is minus 1, upon minus 2 plus 1, which is minus 1, and since this u is with negative sign, so a negative sign will come here. Okay, this negative gets cancelled out with negative, and this becomes 1 upon v minus u from 0 to u. So this becomes 1 upon, okay, let me just write it again, v minus u 0 to u equal to 1 minus cos theta by m rho a t. This becomes 1 upon v minus u, considering with u equal to u, this will become like this, minus u at u, so we'll put u equal to 0, so this will become 1 upon v, and this will be 1 minus cos theta rho a t by m. Okay, so we can solve this. This will become v times v minus u and v minus u, so this becomes plus u, and this term, so let's call it some quantity b times t, where my b is equal to 1 minus cos theta by m rho a, so that we don't have to write it again and again. So then this becomes u is equal to vbt, or it would be better if I just take the reciprocal of this. So this is v into v minus u divided by u equal to 1 upon bt. So this will become v by u times v minus u equal to 1 by bt. This I can take there, so this will become u by vbt. So this will be written as u by vbt plus u, and if I take u outside, this will become 1 by 1 plus 1 by vbt plus 1. This thing implies u is equal to v by 1 plus 1 by vbt. Okay, and this becomes v into vbt divided by 1 plus vbt. Okay, or we can write u by v is equal to vbt upon 1 plus vbt. How would the plot look like? So let's say this is u by v and this is time t. So from here we know that at t approaches to infinity, this u will approach v. Okay, so then u by v will approach 1 at t approaches to infinity. Okay, and at t equal to 0, this is 0, so this will look like this. Okay, so this is the plot of u by v with time t. Okay, so let's briefly summarize what we did in this question. So a problem was given to us that our system was accelerating, and by neglecting friction and air resistance, we had to find how is this velocity of system changing as a function of time. With given the velocity of the fluid and area of the nozzle, we had to find the velocity of the card as a function of time and also had to plot the result. Okay, so we used Reynolds theorem, and since this was an accelerating control volume, we used the equation for the accelerating inertial frame, or for the non-inertial frame. We used this equation, and using these assumptions we arrived at the value of u. Okay, all right.